Okay, in this video, we're going to talk about absolute value functions and how to graph them. There are multiple ways to graph them. I'm going to first show you how to graph them using a table. So that's this problem that I have on the screen. And then I'll show you how to graph it using the transformation. So, sorry about that. So we're going to graph absolute value functions. Just a reminder, this is the original equation. The parent function of the absolute value is f of x equals the absolute value of x. This can also be written as a piecewise function. So kind of like we looked at it last time. If you have a negative, you'll have a negative x out of the absolute value whenever x is less than 0 or equal to 0. And then you have a positive x if x is greater than 0. Now I've went ahead and I graphed this. And I put some information on here so I can talk to you while you write your notes. You can pick any points in the x-axis to see what this looks like. I've found that the best points to use are its vertex and a couple numbers before and after if you're using the table method. And the vertex is always in the equation. For the parent function, it's going to start at the origin at 0, 0. So here's the vertex, and then I used -1 and -2 and +1 and +2. So what I did was I inputted these numbers in the equation. So the absolute value of -1 is 1, the absolute value of -2 is +2. And then that pattern should also happen underneath the vertex, or on the other side of the vertex. So when you plug in a +1, our output is 1. And when you input a +2, the output is 2. This symmetry will always happen because there's an axis of symmetry cutting the graph right down the middle. We should have a negative slope on one side and a positive slope on the other side. They are a mirror image of each other. A couple of other facts about this graph. It has an x and y intercept at 0, 0. That could change if we move the vertex around, so it's important that you know the parent function starts at 0. The domain are all available x's, so I can continue on this way and find x's in the negative direction, and I continue on this way and find x's in the positive direction. So the domain is -infinity to +infinity. But for the range values, I don't use these values on my y-axis. So for the parent function, the range is greater than or equal to 0. And that does get determined by the vertex. So the number in your vertex should be in your range. And then once we get more information, we can graph them from not only a table of values, but from the transformation equation. To be completely honest, I started this video, my screen camera stopped working, so I'm just using the same images. So I have the formula ready for you down here. So we could expand the absolute value function. Remember, it just used to be the absolute value of x. And we can write it using its transformation form. So we have a absolute value of x minus h plus k. And h and k is going to be the vertex. So if you prefer graphing with a table, you can always pull out the vertex and then make a table around the vertex. But something very important here, we're going to start with the middle because our x is the trickiest one. Notice that the equation starts off as a negative. That's because your x's move in the opposite direction that you would think they would. And again, that's because of that negative. The way that I teach it to help people remember is that your x's are liars, okay? They always do the opposite of what you think they're going to do. So in this case, a negative h, you would think it means to shift or translate in the negative direction, but in reality, we're shifting to the right. If it's a plus h, you would think we're shifting to the right direction because that's the positive axis, but we're really moving to the left. And that's all because the equation is built in with a negative. So you can think of it as changing signs, or your x's being liars, or going the opposite way, whatever one works for you. But k does not change. K is a truth teller. It does exactly what it says it's going to do. So if it's a plus k, we're going to move up, shift up. And if it's a minus k, we're going to shift down. And notice I'm saying move and shift. You can use the real words for this, which is translate. It's been translated left and right. It's been translated up or down. Okay, now let's talk about the last letter. But notice I put a box in front of the last letter because there are two options right here in front of the A. You can have a positive or a negative A. And that does something different than the A. So we're going to talk about what happens if this is positive or negative. Well, in the parent function, there's nothing out front of the absolute values. That means it's positive, and that's why our arrows are going to the positive y direction. But if there's a negative sign here, then you're going to have a case where you have reflected over the x-axis and your arrows are going to the negative direction. So if it's positive, your graph looks like a V. But if it's negative, our arrows are down, and we're going to use the negative numbers. Again, this is a reflection in the x-axis. It's been reflected. It's upside down. Okay, now let's talk about the A. If you remember your transformations from pre-cal or algebra 2, you know that this guy changes the slope, or it changes how steep we're going. So in this case, the original function has a 1 here. That's why we have a slope of up 1 over 1 and a negative 1 over on the side. So what happens if I change it to a 2? If I choose a number, if A is greater than 1, a 1.5 or a 2, then we're going to have a steeper graph because it's been vertically stretched. So we stretched out our graph and it has become taller. My slope is steeper than it was before. But if I use a number, now we're not using negative numbers here, right? Because the negative does it has its own job. The A can be between zero and 1. So usually it's a fraction or a decimal. Some number less than 1, but still positive. When that happens, we're going to see that we are less steep. I'm moving not as fast as I was before because somebody has compressed my graph. We've shrunk it together. This is called a vertical compression. Ooh, stuck that word in there. Vertical compression. Now, the best way to do these is to just do them. So we're going to try out some problems here. And if you're totally not getting this, reach out to me or attempt doing it with a table to see if you like that better. Okay, here we go. I got 2 examples for you so you can see some of this in action. My first example is f of x is equal to negative absolute value of x plus 2 plus 3. Okay, now if you're doing the table method, here's your vertex right here. Negative 2, positive 3. So you would put that in the middle, find 2 numbers before and 2 numbers after. But we're going to do transformation method, which actually helps us so we know the vertex is at negative 2, positive 3. So I'm going to go put a point at negative 2, positive 3. There we go. So what happened was our graph was right here. There's the original. Mine's not as perfect as it should be, apologize. So we have a slope of 1, we started at 0, 0. We have a positive and a negative side. Okay, so this plus 2 is really translation I-O-N, maybe? There we go. Translation. It's a positive. So instead of going the positive direction, if you notice here, it went left 2. Okay, this 3 is a translation up 3. So our vertex used to be here at 0, 0. The equation told us, okay, let's move it 2 this way and up 3. So that's exactly what we did. Okay, we're going to check 2 more things before I say that's my graph and I'm done. I need to check the number in front and of A and the A. So there's not a number here. There is a 1 here, so our slope is still 1. We don't have a stretch or a compression, but I do have a negative. So if I go back to my notes, this negative has reflected my graph over the x-axis, and I should make sure to point my arrows down. So this is a reflection over x-axis. So when I draw on my graph, I'm going to still use a slope of 1, so every corner gets a part of my graph here. So technically I went down 1 over 1, down 1 over 1, and over here down 1 over 1, down 1 over 1. That's because there's a 1 here. And then you can connect your dots, and then make sure to put arrows on your graph. So if it's helpful to graph the original, go right ahead, and then we can see how it's been moved to become our function f of x. So 3 transformations happened. We had a reflection over the x-axis, a translation left 2, and a translation up 3. Okay, let's do another one together. If you got it, go ahead and move on. You can do the 4 problems on your homework. If not, stick with me again. I'm going to do it again. This time, g of x is equal to 2 times the absolute value of x plus 6 minus 5. Okay. That should just be a minus 5. I got a little crazy over here with my 5. So, remember the original function started at 0 and it has a positive slope on this side, negative slope on this side at 1. It's not perfect. It's okay. So we're going to go, I go for the vertex first just because, I mean, that's easy for me. Because changing the slope right now is not going to be too helpful. So we need to see what's happening with my x's. How do I move before how do I change my slope? So this is a shift. Six units. And then what direction is that going to be? Well, it's positive. So instead of going positive, remember your x is a liar, we're going to go negative. 6 units left. Okay. The 5 is a shift 5 units down because he's negative. So we're going to go down for that one. Notice that I changed my wording from translate to shift. Either one is correct. For me, I don't mind either one. So I'm going to take my original vertex and I'm going to go 6 left, 1, 2, 3, 4, 5, 6, and 5 down, 1, 2, 3, 4, 5. Ooh, I need to recount that. 1, 2, 3, 4, 5. Okay, so we've moved 6 left and 5 down. Again, you could have started by writing your vertex, and then you could have done the transformations. You can see that it's gone left and down. Now, before I draw it in, I need to check the sign in the front. The sign in the front is positive, so it's going to keep its up arrows. And then the 2 is going to change the slope. That's not what the transformation is called, but that's what it's happening, that's what it's doing to the graph. The transformation is called a vertical stretch by a factor of 2. So vertical stretch by a factor of 2. My graph should be taller and skinnier than my original graph. Not staying, rude. But to graph it, we're going to start at our vertex and we're going to go up 2 over 1, just like graphing a linear function. Up 2 over 1. We're moving with a new slope. Up 2 over 1. And then over here, go back to the vertex to the other side, and it's a mirror image of the other one. So you should have very symmetrical V. You're going to be very good. We're going to use a straight edge to connect our points. Oh, I messed up. Oh well, it doesn't really matter. There we go. So we graphed using a transformation. So this is the graph g of x, and this is the original parent function y equals absolute value of x. So now you can actually see that it shifted and moved down, and that it is thinner than it was before because we stretched it out. Okay, I think that wraps up this video. I'm going to post another video about how to do inequalities so you can finish off your homework, but this should get you the 4 problems. I think it is 9, 10, 11, and 12.